Motors convert electrical energy to mechanical energy with the help of magnets. DC motors are one type of motor and are often used in toys, appliances, and radio-controlled cars or boats. In this simple motor, powered by a battery, the electrical current and magnetic fields make the motor's armature or rotor rotate continuously. To understand this better, we'll look closely at these forces and how they interact. First, we activate this circuit. While electrons actually run from negative to positive, the convention is to think of electricity going from positive to negative, so that's how we show it here. The charged particles in the electrical current create a magnetic field around them as they move, as shown by these blue arrows. Because the copper coil, that is the armature, is part of the circuit, the current also creates a magnetic field around the coil. By passing current through this coil, we've turned it into an electromagnet. As you can see from the way the magnetic field lines in the coil converge, this electromagnet has a north and a south pole, just like a permanent magnet. The electromagnet's field is represented here by a bar magnet. This isn't much of a motor yet though. An important piece, an external magnetic field, is missing. In our demonstration, this horseshoe magnet will provide that field, as shown by these blue lines. We position the horseshoe magnet so that the rotor is right in the middle of the magnet's field. Let's power the circuit again and watch in slow motion what happens between the poles of that magnet. As soon as that current, represented by the red arrows, starts running through the armature, a magnetic field forms around it. Stopping the action for a moment to take a closer look, we see that the field around the coil opposes the field of the horseshoe magnet. Using this bar magnet again to represent the field of the coil, we see here that the horseshoe's magnet's north pole is attracting the south pole of the electromagnet in the armature. In fact, these two magnetic fields oppose or attract each other at several points. Let's talk about how the design of a DC motor leverages these two forces into a machine that can do endless types of work. The current that runs into the armature passes first through one of these graphite brushes, then through one of the two semicircles that make up what is called a commutator, which is a rotary electrical switch made of copper and featuring two gaps. The cleverly designed commutator is key to making the DC motor work. To see why, we'll temporarily replace it with this copper ring, which has no gaps. The bar magnet again represents the magnetic field generated in the coil. As you see, this is still not much of a motor. The interacting magnetic field caused the armature to move, but only to the point when their fields aligned north to south. And there they stayed, opposite attracting opposite, two magnets stuck together. Let's return the real commutator to its rightful place and see what happens now. Notice how one half of the commutator connects to one arm of the armature while the other half connects to the other arm. The current enters the first arm, making the coil spin. But this time, just as the commutator reaches the halfway point of its first cycle, a brush reaches the first gap. After jumping that gap and making contact with the other half of the commutator, it sends current through the other arm of the armature. As a result, current is sent through the coil in the opposite direction. This reverses the polarity of the electromagnet created by the powered armature. So once again, opposites attract, likes repel, and the armature turns another half rotation. As explained by Fleming's left-hand rule, the interaction of the magnetic fields will keep the rotor spinning and spinning for as long as there is current.